Okay, welcome to the second virtual class for Introduction to Computer and Information Sciences with Messiah College. This is the second part of Chapter 7, Problem Solving and Algorithms. So on Tuesday we talked about the benefits of problem solving, the different steps involved with the problem solving process, the use of pseudocode to accomplish algorithms to assist in problem solving, and different examples of algorithms with conditions and loops. So today we're going to talk about different kinds of more general purpose algorithms that can be used for different purposes within broader contexts with problem solving. So remember on Tuesday we talked about how do I use what I already know to solve a problem, to make things happen. And the algorithms that we're going to talk about today are going to be great tools in your arsenal for solving different smaller problems within a larger context. So if you want to be able to sort data in a certain way, but it's stored in a certain data structure, or if you need to locate data in different manners, these are samples of algorithms you can use to accomplish that. So first item on the list today is a search algorithm called sequential search. Sequential search is very, very similar to how we as humans would locate data in a collection. So I believe the example in the book is if you're trying to find data that's stored on an index card. So for example, if you have a recipe, or if you were fortunate enough to be in an older kind of library that had the little cards with information about the books, you could sort through those. Or if you have flashcards that you're studying with, anything like that, then typically how you would find that data is you would simply step through each record in order until you find the one you're looking for. Your stack of index cards does not have to be sorted. It could be in any order, and then you simply would just go through each one until you find the value that you're looking for. So in this way, we can write an algorithm like this. So if you have a variable that's going to keep track of your position, and again, we're going to start at 0 because computers are 0-based, you can iterate through a given array. So let's say numbers, starting with position 0. If the value in the array at that position equals what you're looking for, then you can set this variable found to true, and it will stop executing the loop on the next iteration. Otherwise, you simply increment the position index and move to the next item. Note that the condition for the loop requires that the position variable be valid within the numbers array. So once we either run out of available positions or we find the value that we're looking for, the array will end. So the two possible terminating conditions, either we go through the whole loop and have not found what we're looking for, or we make it through part way and we do find what we're looking for. So either way, the loop will terminate. We do not end up with an infinite loop. So for those of you who are more visual, I am very visual. I found this nifty little GIF online that will demonstrate the sequential search algorithm. So imagine that each of these little columns right here represents a different value in your unsorted array. So the light pink entry is the value that we're looking for, and the red bar simply indicates the one that we are currently evaluating. And you can see it simply steps through the loop, or steps through the array, each item in turn. So it's a very, very simple kind of algorithm. It's not terribly efficient though. So one way that we could make this algorithm more efficient is to sort the array before we search through it. Now, granted, we haven't talked about any sorting algorithms yet, but let's assume that the array that we have is already sorted. So if that's the case, what we can do is read in the value of the array, and in this example here, the values or the lines in red indicate additional modules that we're going to define in a minute. So reading in the array of values, that will be its own module, and then we prompt the user for the value that we want to identify, and then actually perform the search, and if the value is found, then we give the appropriate response. If it's not found, then we give that response. Now, reading in the array of values, very basic little mini algorithm here. Ask the user how many values they want to provide. And then here we have what is called a dynamic array length. So depending on what the user indicates, that's how many elements our array will hold. So that'll be something, if you haven't encountered that in your programming classes yet, that'll be something very useful for you down the road. So once we know how many values the array will hold, then we iterate through the array and ask the user for a value to populate the array with for each element. Like I said, very simple, but the key assumption here is that the user is going to enter the values in a sorted order. So assuming that that actually happened, what that allows us to do is describe the logic of the second little mini algorithm, which does the actual search, and it allows us to short circuit the logic of the loop a little bit. So the idea here is that if you pass the position in the array where the search item should have been and you haven't found it yet, then you can automatically skip the rest of the array. So the difference here is in the second if block. Else if the data of the current index is greater than the search item. That means we've passed the point where the search item was supposed to be, we haven't found it, and we know that every value after this is also going to be bigger than the search item, then we can automatically set the value of the index to the length of the array, which will fail the condition of the loop and cause it not to execute anymore. So this is an example of what we call short-circuited logic, meaning as soon as we encounter a condition that eliminates everything else, then we don't have to worry about anything else. We just stop what we're doing. So if the value is found in the data array, we set found to true, and that will end the execution of the loop. If we pass the point in the array where the value was supposed to be, then we set the value of index to a number that is going to be greater than, well, in this case, it's going to be equal to the value of length so that it fails that first condition and stops the loop. But if none of those are true, then we will increment the value of index and the loop will continue with the next value in the array. So very similar to this, the original sequential algorithm, but now with this extra little bit of logic, assuming that the array is sorted. So a second search that you could possibly do is what is called a binary search. So the idea with this type of search is that if you have your array and the array is sorted, then you can make certain assumptions about the order of those values to cut down on the number of comparisons that you have to do to identify the value that you want to find. So if you start in the middle of the array, then you should be able to assume that all values in the array ahead of the middle will be smaller than the value of the middle, and all values later in the array of the middle will be greater in value than the value in the middle. So when you compare that value in the middle against the value that you are trying to identify, you have information about the rest of the array. If the value is smaller than the value of the middle item, then it will be present in the earlier half of the array, as opposed to the later half. If the desired value is larger than the value in the middle, then it will be in the later half of the array. And in this way, you can repeatedly cut the different sections of the array in half in order to narrow in on the value that you're trying to locate. So here's an example of that. So we're going to start with the first item in the array and attempt to find the last value. So remember, because arrays are zero-based, the index of the first item is 0 as opposed to 1, then the value of the last item in the array, the last index in the array, will be whatever the length is minus 1. So if you have 10 items in the array, the indices, instead of going from 1 to 10, will go from 0 to 9. So first is always 0, last is always length minus 1. And then to initiate the found value, we set it to false. Now, as long as first is less than last, meaning, or less than or equal to last, meaning we're still within the bounds of the array, and we haven't found the target value yet, we're going to determine what the middle is by adding first to last, so 0 plus 9 divided by 2. So in this case, integer division, 9 divided by 2 is 4. So we're going to look at array index 4. So if the search item, the value of search item equals the value of data element number 4 or index number 4, then we'll set the value to true. Otherwise, we reset the values of first and last depending on which half of the array we want to focus on. So we're not actually changing anything about the array here, we're just changing the bounds of what part of the array we're looking at. We're not actually removing elements from the array, we're just changing the index references that we're looking at. So like I said earlier, if the search item is less than the middle value that we're looking at, that means that it is going to be present in the early half of the array. So if it's in the early half, that means that the value of first, being 0, is still good. So we don't have to mess with that. But what we do need to change is the value of last. So in that situation, we now take the value of middle and subtract 1 from it. So if the value is 4, now we're going to look at 3. So we can ignore everything from 4 to 9. Everything else bigger than the value we're looking for, we don't need to worry about it, it's gone. So first is still 0, last is now 3. In that case, we now run through the loop again. First is 0, last is 3, found is still false. So the middle of that, 0 plus 3 divided by 2 is 1. So 1 becomes the middle value, and we run through everything again. And we continue to bisect the array until we find the value that we want. I have another visualization for you. So in this case, we're looking for the green value here. The red bar starts in the middle. The green bar is larger than the middle value, so it moves to the right and continuously works with smaller and smaller halves of the array until it locates the value that it's looking for. I realize this can still be kind of confusing, so I have what is called a trace for you. And this is what a trace is. This is basically desk checking. So this is an example of testing that you would do on paper to double check the correctness of your algorithm. So you could write down a sample data set. So in this case, we have an array of 11 items, and then you can write out the actual values that your algorithm would utilize in order to produce the output that you're looking for. So the data that we're looking for, first, last, and middle, are the different variables that we would use. The comparison that we're using is the value, the comparison value, and then whatever value is at middle. So in this case, it's the actual data in those in that particular array index. And then if there's a return value, then we say what the return value is. So let's say we're searching this list of animal names for the word cat. So notice that the array is sorted alphabetically: ant, cat, chicken, cow, etc., down to snake, and we're searching for the word cat. So the first thing we're going to do is we're going to search the whole array, which means that the value of first is 0, the value of last is 10. So in this case, the middle value is 5, which means that we compare our search term cat to the word dog. Now, cat comes before dog in the in alphabetic comparison, so we can't return anything from the algorithm because first is not greater than last yet, and the comparison does not return is not equal. So we can't return anything. We have to go through the loop again. So now we set the value of last, because cat is less than, we set the value of last to middle minus 1, which is 4. So now we look at the array from 0 to 4, only those values. The middle from 0 to 4 is now 2, so we are comparing the value of cat to chicken. In the same way as before, first is not greater than last, and cat does not equal chicken, so we have to run through the loop again. We don't return anything. So now, because cat is still less than chicken, we now have to look at the array middle minus 1, so it's now 0 to 1. So 0 to 1 is ant and cat, but because of array of integer mathematics, 0 plus 1 divided by 2 is actually 0. So we compare against the value of 0, which is ant. Cat is greater than ant, so first now becomes middle plus 1. So now the array is 1 to 1, which is only one value, and that is the value that we're looking for, so we return true. A second option here, this particular value that we're looking for, zebra, does not exist in the array. So what would that look like? So again, we're starting with first and last, 0 to 10, and the middle value is 5, which is dog. Zebra is greater than dog. So we take the value of middle and add 1 to it, and that is our new first. So now we look at the array from 6 to 10, fish to snake, and the middle value is 8. So we now compare zebra against horse, but zebra is still greater than horse. So take the middle value of 8, add 1, now the new first is 9. 9 to 10 is the new array comparison. And because there's only 2 values and integer division being what it is, the middle value is calculated as 9. So we compare against the value of 9. Zebra is greater than rat, so we go through again. And now we're looking at the last possible value, which is 10 to 10, middle being 10. Zebra is greater than snake. But now when we try to run the comparison again, first is now greater than last. We can't do anything anymore. There is no 11th index value, so now we have to return a value of false. The search returned no results. Zebra is not in the array. So if this is still a little confusing for you, there are many good visualizations online that can help with explaining this concept more. And if you need more help, just let me know. Let Dr. Rohrbaugh know. Algorithms, he loves algorithms. So in moving on from that, those are the two primary search algorithms. We now have some sorting algorithms. Obviously, these two previous algorithms rely on sorted data, if not by necessity, then at least for efficiency. So how do you actually perform sorting? Well, it's a little more complicated than searching. You don't actually have to edit the array at all when you do searching, but sorting does manipulate the contents of the array directly. So the idea here with our first sorting algorithm called selection sort is that you would iterate through the array many times, and each time that you iterate through the array, you return the smallest element that you can find at that point and put it in a new array. This can be very slow. It requires space for two copies of the array, the sorted and the unsorted copy. But it can be very quick and efficient because it's relatively intuitive. So if you had a stack of index cards, for example, and they had Spanish vocab words on them and you wanted to sort them, this is generally how you would do it. You would take your stack and you would flip through and you would find águila, which is eagle, I think. And that's your first alphabetically viable word in the stack. You would then take that card, put it in a new stack, and find the next word that comes alphabetically. Put it in a new stack. The next word, put it in a new stack. So this is much more. This is a much more human way to perform a sort. Again, unfortunately, it does require a lot of space, so we tend not to use it. But for comparison's sake, here is what that might look like. So remember, red text indicates what we're going to extract to its own module here. So while there are elements available in the first array, we will find the smallest element in that array and then move that element to a new array. So we would need 3 distinct new modules for this, and it would basically take care of itself. Now, again, it's not very efficient. It is more intuitive, but there are ways that we could make it better. So let's try this. Make a couple small changes in order to make it more efficient. Let's leave the original array as the only array. Let's not use a duplicate. So start with the first unsorted element in the array, and that's going to be the first time through, it's going to be the first element in the array, so 0. So while the array has not been completely sorted yet, while there are still items to sort, find the smallest unsorted item and then swap it with the first unsorted item, and then increment the unsorted to the next item in the array. So basically what that means is when the first unsorted marker that we have here gets to the last item in the array length -1, that means that we've made it to the end of the array. Now, here's something for you. Why is it array length -1? Why is it not just length -1? So at this point, right. So at this point, we're looking at the decreased value. The last, remember that the length of the array, if you have 10 items in the array, then the last index is 9. So 0 to 9, those are your indices. So why would we not want first unsorted to equal 9? So this is another example of short-circuited logic. So we're going to stop not at 9, but at 8. So once first unsorted equals 9, stop the array. Basically what this means is we don't have to sort the last item in the array. Once 0 through 8 are sorted, element at index 9 is already sorted. It's the last item in the array. You can't compare it against itself. An array of one item is sorted by default. So you can stop one iteration early simply by knowing that the last item is sorted just by default. So how would we find the smallest unsorted item? So we set first the index of the smallest item to the first unsorted index. So the first time around, we're just assuming that the first item in the array, which is also the first unsorted item in the array, they are the same. So first unsorted equals 0, index of smallest also equals 0. So then we're going to look at the first value to compare, which is the next item up the chain. So if we're starting at index 0, now we're going to compare against index 1. So while the comparable index is less than length minus 1, meaning while it's still within the bounds of the array, we're going to look at the data in that comparable index versus the data in index of smallest. So if the value of index is 1, then we're going to compare against the data in index 0. If the data in index 1 is less than the data in index 0, we now change our marker to point to that current index. So now the value of index of smallest is 1. The idea here is that as you iterate through the whole array, you will only reset the value of index of smallest if you find a value, an index element or an array element value that is smaller. So at the end of the array, the index of smallest will stop updating if it is a greater value. It will point to whatever value is the smallest in the array. So assuming that index of smallest now points to the current smallest value in the array, we can swap the first unsorted with the smallest. So if first unsorted equals 0, and the index at which you found the smallest item is 3, then we swap the data in index 0 with the data in index 3. Now, here's a key distinction. If you're going to swap data in two array values, you can't simply set A to B and B to A. The problem here is that once you set the value of 1, you lose the data that was there originally. So you have to have a temporary item to hold one of the values so that it isn't overwritten when you copy in the value of the second. So here we have a temp item which holds the value in first unsorted, which at this point in time is 0, so the data in index 0. And then we set the value of index 0 to be whatever data was in index 3. And then from memory, we take whatever data was in temp item and put it in the index, or put it in the array at index 3. And now they have swapped values. So I understand that this can take a little bit to wrap your head around. So here's another little visualization. So the idea here is that starting at point 0, we iterate through the array, find the smallest value, the minimum, and compare to the original. So now everything to the left of the bar is sorted. Everything to the right of the bar is unsorted. So you can see we identify the minimum each time around and swap with the value that is closest to the unsorted, sorted unsorted line. So there we swapped 3 and 4. Here we're looking at 5, 6, and 4. The minimum is 4, swap with 6, and now we're sorted. There you go. All right. Bubble sort is another possible option for you. This particular brand of selection sort allows you to sort as you go by comparing sequential pairs. So if you're looking at a pair of values A and B, but B is greater than A is greater than B, then you swap. So instead of AB, now it's BA. The issue here is that you will never know if you have completed a full sort just by one pass. You have to complete many passes through the array until you can go through a pass without any swaps. So the idea here is compare 2. 5 is greater than 2, so we swap. 5 is greater than 4, so we swap. 5 is less than 6, so we don't swap. 6 is greater than 1, so we swap. 6 is greater than 3, so we swap. And now we do it again. 2 is less than 4, no swap. 4 is less than 5, no swap. 5 is greater than 1, so we do swap. 5 is greater than 3, so we do swap. But 5 is less than 6, so we don't swap. 2 is less than 4, no swap. 4 is greater than 1. 4 is greater than 3. But it's less than 4 than 5. Or less than 5 and 6. 2 is greater than 1. But it's less than 3. And there you go. That's your completed sort. Now this one is not terribly efficient. It does require you to do, again, many passes through the array, so we're not going to cover the actual algorithm, but I do think that the animation does help a lot to explain. So here's another algorithm we are going to discuss in detail. This is called insertion sort. So again, coming up against the idea that if there's only one item in the array that you're considering, then it is sorted by default. But if you have 2 items, as in the bubble sort, then if they're out of order, you can swap them in order to sort them. But if you extend that array to 3 items, then you already know where you can place that item relative to the relative to the previous 2 in order to sort the array of 3. So that's the underlying principle here. So we're going to start with the array with the first item on the left. It's already sorted. We don't have to worry about it. Expand to the leftmost 2 items. If the first item is greater than the second, then we swap. Okay, great. So now the first 2 items are sorted. Expand to the third item. If it's not in order already, where can we place it in relation to the first 2 in order to make sure that it is sorted? And this is what that algorithm would look like. If you start with the current index is 1, because again, we don't have to worry about the first item. 0 is sorted already. Then as long as current is less than length, look at the next index. So if current is 1, then look at index number 1. If index is greater than 0, which it is, and we haven't found anything yet, then compare the data in index number 1 with the data in index number 0. If 0 is greater than 1, if the value in index 0 is greater than 1, swap them. And then set the current index to 0. So then we're going to increment current and go back up. Current is now 2, and we're going to look at index number 2. Set place found to false. It is. We're going to look at index 2 and index 1. And now with index being 2, we're going to compare the third item and the second item. How do they compare? If 3 is greater than 2 or 2 is greater than 3, swap is necessary, and continue. So again, this is something that's a little more intuitive with an animation. So starting here with the sorted unsorted bar again. So there you go, swapped to. The actual description or watching the animation is a little more intuitive than dealing with the algorithm itself. So the idea here is that you would not have to recreate this logic yourself if you were trying to use it in your own algorithm. As long as you are familiar with the principles of the sort itself, so that you can identify situations in which it would be helpful to you, then you can pull this algorithm in as a resource so that you're not reinventing the wheel. So I mostly want you to be familiar with the principles in practice, the differences in how they operate at a high level. I'm not going to ask you to recreate these algorithms yourself. Selection sort, insertion sort, bubble sort. So just being able to describe the differences between them as opposed to delineate actual pseudocode to describe how they're accomplished. Now, there are certain problems that cannot be solved by brute force. And one of the solutions that we have for problems like that is this concept called recursion. Recursion, the best definition that I heard was C definition of recursion. So the idea here is that recursive logic is a block that calls itself. And there are definitely questions in your mind right now, I know there are, on how this could ever be useful. And really, the answer is that this allows us to subdivide a task by applying the same functional logic to a smaller data set. So if you have this function that you don't know how many times you're going to have to use it, you can replace a loop with a recursive function call. Now, what this requires from us is we need to be very, very intentional in how we set up this code. It's very easy to get lost in a recursive loop. It's very easy to introduce an infinite loop, an infinite recursion call into your code without meaning to. But if you can pull it off, it's a very powerful tool in order to process large data sets. So the different types of recursive or different types of function calls that you could do, the book refers to them as subprograms. You can either have a void subprogram where you call a different method or a different function or a different procedure, and then it simply returns back to the main program. It doesn't actually give you any data, it simply does the function that it needs to do and then comes back. There's also a value returning subprogram, which gives information back to the program that called it. So in this case, if you have a numeric result, subprogram B returns a number and the original program adds it to 5 and then keeps going, that kind of thing. Recursion operates on both of these principles. So what you want to have a base case that returns a value, some finite ending value, and then builds on that by calling it again and again to construct an aggregate result. So here is a basic recursion example. This is a wonderful first look at recursion. If you've encountered factorials in math class before, remember that the factorial is basically n, factorial of a number n is every value times itself from 1 to that number n. So the factorial of 5 is 1 times 2 times 3 times 4 times 5, which is 120. So the idea here is that for any number that the user provides, we should be able to follow the logic of the factorial to produce a result. So for any number that the user gives, feed it into this factorial module and perform the necessary calculation. So, for example, let's use the number 5. So factorial of 5, we compare 5 to 0. 5 does not equal 0, so we execute the else block, which says return the number 5 times whatever result you get of factorial of 5 minus 1, which is 4. So go back up to the factorial call again. Factorial of 4. 4 does not equal 0, so go to the else block and return the value of 4 times whatever the result of factorial is of 4 minus 1, which is 3. And then 3 returns 3 times factorial of 2. 2 returns 2 times factorial of 1. 1 returns 1 times factorial of 0. Now we have an interesting situation. So in this case, n equals 0, so we return a value of 1. This is our base case. This is how we can prove that the loop actually ends. So we return a value of 1, which if you can picture in your mind, 1 is returned to the call of factorial 1. So in that case, the return value is n times factorial 0. N is 1, factorial of 0 returns 1. So now that expression is 1 times 1, which is 1. Now that value of 1 is returned to the factorial call above that, which was 2. The factorial of 2 returns 2 times factorial of 1. Factorial of 1 is now bubbling up as a value of 1. So n times 1, 2 times 1, returns a value of 2. 2 bubbles back up to the factorial of 3. Factorial of 3 returns n times factorial of 2. Factorial of 2 equals 2. 2 times 3 is 6. The value of 6 bubbles back up to the factorial of 4, which is 4 times the factorial of 3. 4 times that value of 6 is 24. Value of 24 bubbles back up to the factorial of 5. 5 times 24 is 120. So you can see how it's very easy to get lost in recursive logic that loops through again and again and again with different conditions. But if you can identify a situation where recursion is appropriate, such as a factorial, then you end up with this very, very powerful tool, which is able to accomplish quite elegant logic with only a few lines of code. So remember back to the binary search, which chopped an array in half every time you wanted to find a value within the array. So let's define a module called binary search, which inputs the value of first and the value of last. So these define the array, the span of array entries to compare against. So if we start with first is 0 and last is 10 or 9, then we can set the appropriate middle value, compare against the data in middle value, and if we found the value that we're looking for, then we can return true. And that is going to be the base condition here. That's the second base condition. The first base condition is when we find a value of first that is greater than last, meaning that we've iterated through all elements in the array and there are no more to compare against, then we return false. So that's the first condition. The second condition is we actually found the search item that we're looking for in the value of data middle, and then we return true. So these are our proofs or our verifications that the loop will not run forever. So assuming that first is still less than or equal to last and we haven't found the search item yet, then we can call our binary search method again with updated first and last values. So the first condition down there, binary search first and middle -1, that gives us the early half of the array relative to first and last. And the second, call binary search middle +1 to last, gives us the second half of the array. So then when you run the binary search function again, first and last have these updated values. Now, this is very similar to the factorial algorithm that we looked at before, but instead of the loop logic where the results compound against each other, we're actually just returning a single value. So instead of bubbling up all of those numbers, performing all of these calculations, we just return true or false once. The difference here is that when you call binary search, it just simply returns a value. It doesn't do value times whatever like it did in factorial. We just return either true or false. Makes it a little easier. So here is an algorithm, an entirely new algorithm that requires recursion to work completely. Binary sort you can do without recursion if you really need to, but quicksort you cannot do without recursion. Cannot do it at all. It operates on a very basic strategy of divide and conquer. So the idea here is that if you can split up an array into smaller and smaller halves, then you can eventually get down to the point where there are only pairs to compare and swap. And then by building back up from the pair comparison, you will have a fully sorted array. So here's the basic high-level algorithm, again, starting with first and last, which will change over time. You select what is called your split value, which is basically the halfway point. Think of it of a halfway point. It's not going to be the halfway every time, but it is at least the point where we're going to split the array for further sorting. So we select the value that we're going to split on. We're going to split according to that value. This returns the index of that value, which we call the split point. So the split value is the actual number that's stored in, or the actual string, or the data value in that element array, in the array element. And then the split point is the index of the array element where that value was found. And so you can then sort each half, quote unquote, according to that split point. This is, like I said, recursion takes some time to wrap your brain around, so don't stress if this is confusing for you. Recursion takes a while to get. So the goal here is to, like I said, to split into halves. They're not going to be equal, but at least to split according to whether or not the value that you found is greater or less than the other values in the array. So to split according to the value that you've provided, really, this logic, it's not going to be particularly intuitive. This algorithm was somebody's doctoral thesis, so don't worry if you don't get this right away. We're going to just punch directly to the little animation here. So they select their split value from the right side of the array in. So if you have the value 31, then we're going to find the point in the array where though that value would become the middle. So starting from the leftmost point of the array and the rightmost point of the array relative to the pivot, we then swap pairs of the array left and right, right and left and right, right and left, until they are sorted relative to that pivot value. So you can see here, 26 and 35 comparing 33 and 27, that was less, so they split. 42 is greater than 19, so we swap. 10 is less than 14, so that's fine. All right, and that is where the pivot point would go relative to everything else. And from that point, assuming that the pivot value is in the right place, then we perform the algorithm again. Everything to the left is now sorted in the same way. Everything to the right is now sorted in the same way. It's a very involved process, but very efficient from a computing standpoint. So I'll finish this one more time. All right, and then everything to the left of 31 and everything to the right of 31, we now quick sort again. Okay, so again, I don't expect you to be full experts in these, in the actual implementation of these search and sort algorithms. Just be familiar with the high-level principles and to describe the differences between them. I will not ask you to actually write out how they work in specifics, just be able to describe the differences between them. Okay, so basically what we've seen here are concepts of abstraction. So the idea being that you as a programmer, as a student, the folks reading your code, the folks using your code, nobody needs to know everything all at once, all the time. So we have this concept of information hiding, which means that we obscure details of the implementation in order to maintain our focus and awareness relevant to whatever task we're trying to accomplish right now. So if you go back to any example, any algorithmic example that we've looked at so far, where we split out logic to a separate module, that is an example of information hiding. If somebody wanting to determine the dress code for a given temperature, then they don't need to necessarily know how the temperature comparison happens. They just want to see that you can request a temperature from the user, determine what the dress code should be, and then output the result to the same user. The actual details of determining the dress code aren't as important. We don't necessarily need to know. So we can pull that information out, put it in its own module, and edit it separately. So that in and of itself is a concept of abstraction. The idea that we can replace complex details with high-level descriptions in order to meet different people's needs. So if you are a sports fan and your significant other is really not a sports fan, you can describe the details of a football game without having to go into complex discussion, because you know he or she just doesn't understand, doesn't care, they're not as familiar, they don't need to know every little nitty-gritty thing. But maybe your opponent in your fantasy league, you just want to rub it in on how you picked this particular running back this week and how they just beat the crap out of them, and so now you get into a different level of conversation than you would have with your significant other. If your significant other does actually enjoy football, that's awesome. Maybe they're your opponent in your fantasy league. But proper division of labor between hardware and software components is key for maintaining organization. So both within your code, for different users, for different stakeholders on your team, the different levels of documentation you have to provide. This practice of abstraction and information hiding becomes very, very important as you pursue different career paths within computer science. So part of the benefit here is that if you have abstractions, then when something breaks or you have to change the implementation, the low-level details, then the other components can respond appropriately without being too dependent on information that they don't necessarily need. So think of a file system on your computer. You could, if you wanted, just leave all of your documents on your desktop. You could, technically you could. But why? You organize your files in folders because you want to know where things are. You want to have organization, you want to have order, but also just for general use. So if you know that different assignments are due at different times, or if you know that this particular reference folder is going to be used for your for whatever game you're playing or for this new development project that you're working on, files and folders can depend on each other without needing to know exactly what's inside. So it's that kind of thing, but again, it will become more important if you enter a software development kind of position in your career. Getting a good handle on appropriate relationships between different software and hardware modules will definitely serve you really well. So different kinds of abstractions that you might or might not be familiar with. The first is data abstraction. So separating how data is stored from how it is used. So for example, I think the example they gave in the book, if you have an account at a bank, you don't really care how, as a person, as a human person, you don't really care how the bank's software stores your account information, whether it's twos complement numbers or ones complement numbers, or if they have a punch cards or if they're all written out by hand. You don't really care how that data is stored. You just care that when you go to get information about your account or go to get money out of your account, that all of the data reflects the appropriate status of your account. You don't care how it's stored, you just care how you use it. So that's data abstraction. Procedural abstraction, that's pretty much what we've been doing so far. Separating out modules, different components of complex tasks from how they're actually used. So with the dress code determiner logic, the actual steps taken to evaluate a temperature and return a dress code, that is its own little nugget of logic. How it is actually used can differ. So if one programmer wants to have the standard input-output that we saw before, that's up to them. Maybe this programmer over here wants to use that logic as part of a larger weather tracking application and isn't going to use that direct user input and output that the first guy wants. So separating how a task is actually accomplished versus how it's used, that's procedural abstraction, and that will become very important for you with programming assignments down the road. So finally, control abstraction is a little different. So this is more dependent on the computer itself as opposed to you as a programmer. So with the logic of a control structure like an if statement or a while statement, you as the user don't need to know how the computer evaluates that structure, that program flow concept. So you know what an if statement is, you know what you want it to do, you know what the expected output is supposed to be, but you don't need to know how the computer gets it done. What's even better is you expect an if statement written in Python to operate with the same general output and consistency as an if statement written in C or JavaScript or Java or any other fill-in-the-blank programming method. The idea of a high-level control structure being implemented in every language that exists is a common thing that you expect to have behave consistently, but you don't need to know exactly how that happens. All you need to know is that it does work and you can use it. So that's a control abstraction. And again, these kinds of concepts will continue to come up with different programming, database, project management projects that you will work on through your career, but just make sure that you are aware of the different kinds of abstractions so that you can address them appropriately when the time comes. Okay, so this is chapter 7. So we've covered what algorithms are and why they're important, different steps and strategies for problem solving, the use of variables, controls, conditionals, loops, and things in pseudocode. We've covered different types of searches and sort algorithms, the nature of recursion, and the benefits of different types of abstraction. So again, I apologize for those who are not really seeing themselves pursuing a programming kind of career, but be aware that these are still very general purpose concepts and they can still help you a lot in any career path that you choose to pursue. Okay, so just a quick reminder, the homework for this week is the programming game. So if you haven't had any programming experience up to this point, I encourage you to try Hour of Code. If you have had programming experience, then I encourage you to try out Code Combat. There are at least 20 levels that I would like you to complete. The proof that I would like to see is listed in the assignment description on Canvas. Remember, this should be a relatively quick and painless exercise, so just something fun to play around with, to practice your problem-solving skills. But please make sure that you submit your verification to Canvas by Tuesday, October 18th. So I will see you in class on Tuesday. Please remember to read Chapter 10 and take the quiz before class as well. Have a great weekend. Can't wait to see you guys. I will talk to you later.